All right, welcome everybody. Today we are going to talk about lesson number 9. So this is section 2.2, which are the basic differentiation rules. As of now, in lesson 8A and 8B, you were first introduced to the concept of a derivative. And the only way in which you're able to find derivatives so far is by using the limit definition. While that is a perfectly good way of finding the derivative, and it is very important that you're able to do that, at least at first, there are, of course, some shortcuts. In fact, there are a lot of shortcuts, several of which we're going to write down today in our notes. But hopefully your teacher has also posted for you a copy of the formula sheet for the year. It has all the rules for differentiation, which you're probably going to want to find that sheet and print it out because you're going to want to refer to it for the next several chapters. So I would recommend you do that sooner rather than later. So what are the basic differentiation rules? Well, basically, they're shortcuts for finding derivatives without the limit definition. So from this point forward, unless the problem specifically says find the derivative using the limit definition, then you are allowed to use these shortcuts. So most of the time you will be using them. We're going to focus not only on the rules, but also on the notation. So it's kind of important that you're writing down everything exactly as I'm writing them down. And then, of course, ask your teacher questions when they pause the video. I'm going to try to zoom in here on the important stuff so that everybody can see it, whether you're watching it at home or whether you're watching it in class. So the first and most basic rule is called the constant rule. You don't really have to know them by name. Your teacher will most likely refer to them by name, but after a while, it'll kind of just become instinct. So what the constant rule says is that the derivative of any constant is 0. And you saw examples like this in the last homework where you went to take the limit definition of 7 and it turned out that the answer was just 0. So the reason why is because the derivative of any constant is 0. Here is what that would look like in terms of a formula. So in terms of a formula, we would say that d dx, and that means the derivative in terms of x of any constant c would be equal to 0. So again, that is the constant rule. In terms of what the d's mean, the d over dx means the derivative in terms of x of any constant is equal to 0. If you're wondering, are you ever going to take a derivative of something not in terms of x? The answer is yes, but not for several sections. So notice here that in our first set of problems, each of these functions is in fact a constant. 7, 0, -3, and even pi squared, those are all in fact constants. So without a doubt, the derivative of each one is 0, but I just want to go ahead and focus on the notation. So if your problem starts off as y equals, you have two different options for what you can call the derivative, the first of which is dy dx, and so of course the derivative is 0. If you have f of x, the derivative of f of x is f prime of x, which again, in this case is still 0. Let's say your function is s of t. The derivative of s of t is s prime of t, which again, still 0. And then when it comes to y equals, you either have an option. You can either call it dy dx or you can call it y prime. But again, because all of these examples are constants, the derivative of each one is in fact 0. Again, if you're wondering, how do I know when to use dy dx versus how do I know when to use y prime, that will all be talked about later in the chapter. And for now, it's up to you to choose whichever one you want if it's y equals. So pretty easy there with rule number 1. The derivative of any constant is in fact 0. So now let's go ahead and talk about some slightly more difficult problems. And in order to do this, we're going to need something called the power rule. So here is the power rule. If you are taking the derivative in terms of x, which again is d over dx, of x to the n, which basically means any variable raised to any power, you're going to go ahead and bring the exponent down to the front. Then you're going to take whatever the exponent was, and you're going to raise it to the 1 less power. So again, the way you would describe that in words is you would take the exponent, move it down to the front, then take the variable and go to the 1 less power. So let's take a look at our first example here. F of x equals x cubed. If you're going to take the derivative of f of x, you're of course going to call it f prime of x. Based on the formula here, you're going to bring the exponent down to the front, which would be 3. You are then going to take the exponent to the 1 less power. So 3 minus 1 would give you a 1 less power of 2, which means that the derivative is equal to 3x squared. For number 2, and honestly for a lot of these problems, before you take the derivative, you're often going to have to do a rewrite step. Notice that right now, the cube root of x, that is not technically written as an exponent. Of course, you can rewrite it as an exponent, which is, of course, what you would want to do. So you would want to start by rewriting the cube root of x as x to the 1/3 power. Once you write this as x to the 1/3 power, now you're going to go ahead and just follow the rule. So the derivative of g of x is g prime of x. You're going to bring down the 1/3. You are then going to take the variable to the 1 less power. So 1 less than 1/3 is 1/3 minus 3/3, which would be negative 2/3. We don't really like to leave our answers with negative exponents, so we're going to very carefully give our answer. The 1 is going to remain on the top of the fraction. There's a 3 in the denominator, and then the x to the 2/3 is going to move to the bottom as well. So the derivative here is equal to 1 over 3 times x to the 2/3. Number 3 is a kind of similar. So right now, because I have the exponent in the denominator, that's not really the best way of writing this problem. So again, I'm not writing in the derivative box because I haven't actually applied the rule yet. All I'm doing over here on the left side is doing the rewrite step. So I'm going to start by rewriting this as x to the negative 2 power. The derivative of y in this example, I'm going to call dy dx. I'm going to bring down the exponent, which is negative 2. I'm going to very carefully go to the 1 less power, and 1 less than negative 2, be careful, is negative 3. And then again, in my final answer, I'm going to clean it up. So the negative 2 is going to remain in the numerator. I'm going to move the x cubed to the bottom, which will then, of course, make it positive. So my derivative in this case is negative 2 over x to the 3rd. All right, let's go ahead and talk about the next set of rules. So the next set of rules is something called the constant multiple rule. And the constant multiple rule says the following. If you are taking the derivative in terms of x, so d over dx, of a constant times a function, then basically you're allowed to just leave the constant out front and then take the derivative of f. Here's the thing, these two rules, the constant multiple rule and the combo rule, kind of go together. So you'll see the examples are 1 through 6 instead of being two separate things. But again, the constant multiple rule says that if there's a constant out front, leave it there and then take the derivative of the function as you normally would. So take a look here in number 1, y equals 5x to the 3rd. If you were going to take the derivative of x to the 3rd, you would do it using the previous rule, the power rule. Because there's a 5 there, you're just going to leave the 5 out front. So the derivative of y in this case we'll call y prime. You're going to leave the 5. For x to the 3rd, you're going to bring down the 3. Then you're going to raise the exponent to the 1 less power. Simplify by multiplying, which means that your derivative in this case, y prime, is 15x squared. For number 2, it might not look like there's a constant there, but there is. You, of course, are going to start by rewriting this as 2 times x to the negative 1. Let's call this one dy dx. And again, for now, you can just use them interchangeably. It will matter, but not yet. So again, you're going to go ahead and leave the 2. You're going to bring down the negative 1. You're then going to raise the exponent to the 1 less power, which again, very carefully is negative 2. If you go to simplify that, you're going to leave the negative 2 in the numerator, and you're going to move the x squared down to the denominator. So 3 through 6 are just kind of an offshoot of this rule, and we call it the combo rule. Oops, sorry for the motion there. So what the combo rule does is it basically combines the power rule and the constant multiple rule just to kind of write it a little more cleanly. And here's what it says. If you're taking d over dx of a constant times x to the n, You're going to leave the constant out front. You're going to multiply it by whatever the n is, and then you're going to just take your x and go to the n minus 1. So basically what we did in examples 1 and 2, but it's just kind of formalizing the process if you don't want to kind of show that extra step. So again, leave the constant out front, bring down the exponent and multiply them, and then move the x to the 1 less power and simplify. For almost every problem, you are first going to want to focus on what I call the rewrite step. I would suggest that if you're doing a rewrite step, you leave it for now in the function box and only move it over to the derivative box when you've actually applied one of these formulas. So 4t squared divided by 5, if you rewrite this problem as 4/5 t squared, it becomes much, much easier to see how the rule applies. So because this is f of t, we're going to call the derivative f prime of t. You're going to bring down the 2. You're going to multiply it by 4/5. That's going to give you 8/5. You're going to take t squared to the 1 less power, which would just be t to the first. You can put a little first there if you want to. Otherwise, 8/5 t is perfectly good. For number 4, again, there's a rewrite step. Instead of the square root of x, we will write that as the equivalent 1/2 power. We'll call this derivative y prime. So you're going to go ahead and bring down the 1/2. 1/2 times 2 is 1. You're then going to go x to the 1/2 to the 1 less power. 1 less than 1/2 is 1/2 minus 2/2, which would be negative 1/2. And then in your final answer, you're going to leave the 1 in the numerator, and you're either going to leave x to the 1/2 in the denominator, or sometimes you will see the answer rewritten as a radical. It actually doesn't matter in this case which of those you choose. I know that in the past you're not supposed to have square roots in denominators, but when it comes to calculus answers, we really don't care. Number 5, again, looks like a complicated problem, so the rewrite step is extremely important. So you're going to first go ahead and rewrite this as 1/2. Then you're going to take the cube root of x squared. The cube root of x squared can be written as x to the 2/3. And then the only way to move it up to the numerator would be to write it as x to the negative 2/3. The derivative of y we'll call y prime. So you're going to multiply the negative 2/3 times the positive 1/2. That will reduce the 2's and give you negative 1/3. X to the 1 less power. So 3/3 less than negative 2/3 is negative 5/3. And again, when it comes to your answer, make sure it is clear what's in the numerator and what's in the denominator. So in terms of the numerator, the negative 1 should stay there. The 3 should move or stay on the bottom rather, and then only x to the 5/3 moves down. You want to make sure that you're only moving things that do in fact have negative exponents. So negative 1 over 3x to the 5/3. For number 6, you're going to go ahead and rewrite this as negative 3/2 times x to the first. And again, it's usually just good to remind yourself that there is a 1 there. So now we're going to call this dy dx. And again, for now, use that notation interchangeably. You're going to bring down the 1 times negative 3/2 is negative 3/2. You're then going to bring x to the 1 less power, which would be 0. And hopefully you remember that anything to the 0 power is, of course, just equal to 1, which makes your final answer here simply negative 3/2. So those are your first 4 rules: the constant rule, the power rule, the constant multiple rule, and the combo rule. And again, the constant multiple rule and the combo rule kind of go together. And then the sum and difference rules are actually quite simple. All the sum and difference rules basically say is that you're allowed to do all of those rules for as many different terms as exist in your polynomial. So if you're taking the derivative d dx, and just, so you know, it's only going to be d dx, at least for today. If you're taking the derivative of some function x added to or subtracted with some second function g of x, the rules for derivatives say you're allowed to take the derivative of the first thing, then add it or subtract it with the derivative of the second thing. And you could do this for as many things that are being added or subtracted in your polynomial. So again, all it really means is that you're going to take the derivatives one at a time. So let's take a look here at our next example. So our next example is x to the third minus 4x plus 5. There's no simplifying or rewriting to do other than to remind yourself that this is x to the first. So I'm going to jump right to the derivative step, which is to call it f prime of x. And you're just going to take the derivative one at a time. So the derivative of x cubed, bring down the 3, x to the 1 less power. Negative 4x, whenever you have just x to the first, the 1 less power is always going to be to the 0. So the derivative of anything times just x is whatever the constant is, which in this case would be negative 4. The derivative of the constant 5 is just 0. So your answer is 3x squared minus 4. It's basically just like doing the examples that we just did, but all in the same problem. Then if you flip to the back, you'll see a couple more here. So negative x to the fourth over 2 plus 3x cubed minus 2x. Again, really the only thing that I would recommend is negative x to the fourth over 1/2. I would rewrite that as negative 1/2 x to the fourth. It just helps to kind of separate it a little bit so you know exactly who is the constant and who is the variable. So we're going to call this g prime of x. If you bring 4 times negative 1/2, that's going to give you negative 2. X to the 1 less power would be 3. Plus, bring down the 3 times 3 is 9. To the 1 less power would be squared. Negative 2x, again, whatever you're taking the derivative of something times x, it's always just whatever the something is, which in this case is negative 2. Now, don't get too fancy when it comes to the derivatives. There are eventually going to be problems that you have to factor and simplify and solve for x, all kinds of things. But for now, don't get fancy. You're just going to go ahead and leave it. Finally, if we take a look here for number 3, so right now it looks like a quotient, looks like a division. How do you take the derivative of something with a quotient? Well, you haven't learned that yet. So as you go to do tonight's homework, if the problem looks like something that you haven't learned a rule for yet, that means you have to go ahead and rewrite it. The way that you would rewrite it here is, I don't know if you remember back in the day, the heart here. Basically, if you have more terms on the top as opposed to the bottom, you're allowed to break it up, each numerator over the denominator. So that would give you 3x squared over x minus x over x plus 1 over x. Then again, we're still not ready to take the derivative. We have more simplifying to do. So that's why I've stayed over here in the left-hand box. So 3x squared over x, that simplifies to be 3x. X over x simplifies to be negative 1. And then plus 1 over x, you're going to rewrite as x to the negative 1/2 power. Again, the whole point of this rewrite step is to make sure that you are writing it in the way that it's easiest to find the derivative for. So I need a little more room here. Go over to my other side now. So because this was a y equals, again, you can call it y prime or dy dx, and you simply do it one at a time. The derivative of 3x is just 3. The derivative of the constant, negative 1, is just 0. The derivative of x to the negative 1, you would bring down the negative 1, and then x would go to the 1 less power. If you were to simplify, which you should to get rid of the negative exponent, you're going to get 3 minus 1 over x squared. That would actually be a fine answer for now, but at some point you might be asked to find a common denominator. And if you are asked to find a common denominator, it would be x squared, which would give you 3x squared minus 1 over x squared. Again, for the moment, we would accept either of these, but of course, good to know that they are in fact equivalent. So again, sum and difference rules are basically just take the derivatives one at a time. This next set of boxes here, you're using the rules that we've already gone over, but we're really just kind of trying to show you what is important in terms of when you rewrite it, when there are parentheses. So you'll notice that 1 and 2 look almost the same aside from the parentheses. 3 and 4 look almost the same aside from the parentheses. And believe it or not, those parentheses are actually quite a big deal. So it is important that when you rewrite it pretty precisely. So in the rewrite step for number 1, 5 over 2 x to the third, the very best way that you can rewrite that is y equals 5 halves times x to the negative 3. Then for number 2, the best way that you can rewrite this is by actually cubing the denominator and then simplifying. So if you cube the denominator, you're going to get 8x cubed. If you have 5 over 8x cubed, you're going to write that as 5/8 x to the negative 3. For number 3, 7 over 3x to the negative 2, the way that you're going to rewrite that is you're going to leave that as 7/3. And then when you bring the x to the top, it's just going to be x squared. For number 4, because you have 3x, the whole thing raised to the negative 2, if you first go ahead and square the denominator, you're going to get 9x squared, still to the negative 1, because all I did so far was square it. The fact that this whole thing is raised to the negative 1 means that the whole thing now needs to move up to the top. So you're going to leave the 7 on the top, bring the 9 up, which is going to become a 63. You would have x to the negative 2, which would move to the top, which would become x squared. So I think you can see here in the rewrite step, while the problems looked very similar to start, they look pretty different when you rewrite them. There's only a handful of problems in the homework that require you to kind of go through this entire process, but we do think it's important. So I wouldn't blow it off, at least not until you get more familiar with these types of problems. So now we're going to go ahead and actually do the differentiate step, which means we're going to go ahead and do the rules. So here in the first one, you're going to bring down the negative 3, which if you multiply it by 5/2, so we're going to leave the 5/2 outside. We're going to bring down the negative 3, which gives me x to the 1 less power, careful, is negative 4. Here in number 2, leave the 5/8, bring down the negative 3, again, careful, to the negative 4 power. For number 3, y prime is going to be equal to, leave the 7/3, and then you're going to bring down the 2, and x will go to the 1 less power. And here in the last one, you're going to leave the 63, bring down the 2, and again, x to the 1 less power. Last but not least, you want to simplify. And for now, your main goal when you're simplifying is just to ensure that you don't have any negative exponents. So here in our final step of the first one, we're going to go ahead and multiply 5/2 times negative 3. That's going to give me negative 15 in the numerator. That's going to leave a 2 in the denominator. And I'm going to move my x to the 4th down to the bottom. Let's write that a little bit more neatly. Okay, then here in number 2, again, winds up being pretty similar. You're going to get negative 15 over 8x to the 4th. In the third one, so 7/3 times 2, that is going to give you 14/3. And again, make it clear that it's 14 on the top, 3 on the bottom, and then you can either write the x with the numerator or write it as 14/3 times x. Either of those would be fine. And then last but not least here for this section, 63 times 2x, that's just going to simplify to be a nice 126x. So sometimes parentheses matter way more than others, as you can see in the first two, not all that different. As you can see for the last two, very different. So again, it is important that you pay close attention to those parentheses, and you will just have a small section of your homework tonight that does that. Finally, the last of the easy and the most straightforward rules are how do you take the derivative of the sine and cosine. There is a reason why they are the way they are, which I'm sure your teacher would be proud and happy to show you. Otherwise, you can just take my word for it, which is that the derivative always of the sine of x is always, always, always the cosine of x. And the derivative of the cosine of x is always, always, always the negative sine of x. And yes, there's a reason why it's negative as opposed to positive. We'll talk a little more about it in later sections, but again, for now, I'm pretty sure you'll be happy to take my word for it. And if you're wondering, yes, there are derivative rules for the other trig functions as well, but we're just going to go ahead and start with the sine and cosine. So for our last couple of examples here, notice that you have sine and cosine kind of mixed in with all the other functions. So treat the problems exactly as you would up until this point, but now just don't forget that the sine and cosine are a thing. So here in number 1, y equals 2 sine of x. There's nothing to rewrite here. So as I go to take the derivative, which I'm going to call y prime, I'm going to leave the 2. The derivative of the sine of x is the cosine of x, and that's my answer. Nothing to simplify, nothing else to do. The sine of x over 2 would be better if you wrote that as 1/2 sine x. The derivative y prime is 1/2 times the cosine of x. And again, perfectly fine answer. Here in number 3, remind yourself that this is x to the first. As you now go to take the derivative of x to the first, you would bring down the 1. The x would go to the 1 less power, which would be 0. So the derivative of 1x is just 1. The derivative of the cosine of x is the negative sine of x. So your answer here would be 1 minus sine of x. Final problem here of the lesson, you have 1, 2, 3, 4, 5 terms here in your y equals, and you're simply just going to take the derivatives one at a time. So the derivative of cosine is, of course, a negative sine. The derivative of negative pi over 3 times the sine of x. Pi over 3 looks a little funny, but that is still just a constant. So the derivative of a negative pi over 3 times the sine, leave the negative pi over 3. The derivative of a sine is a cosine. The derivative of 4x squared, bring down the 2, times 4 is 8 to the 1 less power x. The derivative of negative 6x is negative 6, and the derivative of a constant 5 is, of course, just 0. So those are what are considered to be the basic straightforward rules as far as differentiation goes. Obviously, if you do print out that formula sheet, you'll see there are many more, all of which are coming. So here is homework 9, section 2.2 in the book, page 114. And all of them are simply exactly like your notes. They all say take the derivative. So I would strongly recommend you have this note sheet in front of you. You have your formula sheet in front of you. And to be honest, I think you should find this assignment quite manageable.